Hello everyone, and welcome to today's chem lesson. Today, we're going to spend some time talking about how to balance an equation and what it means when an equation is balanced. Now, before we even look at any equations, we want to reinforce this idea that when an equation is balanced, it correctly follows the law of conservation of mass, which says that matter cannot be created or destroyed. It can only change forms. So that means that if we have an equation, something like this, we want the same amount of each atom on the left side of the arrow and on the right side of the arrow. So that means if I'm looking here at this equation specifically, I have 2 hydrogens on the left, 2 hydrogens on the right, 2 oxygens on the left, 1 oxygen on the right. There's an imbalance in the oxygens, which means that if I read this literally, I destroyed an oxygen atom in order to make this reaction happen. And that cannot be correct, right? That cannot be true. So we need to balance this equation by putting numbers in front of each individual substance. Right? These are the only spots, these purples are the only spots that I can put numbers in this equation. You are not allowed, let's go here, you are not allowed to change subscripts. Right? You're not the person who dictates whether or not this compound is water or peroxide, right? You can't change the numbers in the compounds themselves. You can't choose to split H2O into H2 plus O, right? You don't have the power to make that decision to split these into 2 different things. The only thing that you can do is work to balance this equation by putting coefficients in front of each unique substance. That means things separated by a plus sign or things that come directly after an arrow or directly before an arrow. So I can put 3 numbers here. In this case, in order to balance out my equation, I need to put a 2, a 1, and a 2. That is going to mean I have 4 hydrogens on the left, 2 oxygens on the left, and then here with 2 waters I'm multiplying. I have 2 copies of H2O. So 4 hydrogens and 2 oxygens. These numbers are the same for each atom, which means I have correctly balanced this equation. As soon as we see any amount of any element, we know it needs to be the same on both sides, and we can mess with those numbers a little bit to make sure that that happens. Let's look at another example and take it a little bit more slowly, a little bit more step by step. Here, we've got another equation. Right? I've already put the underlines where we are allowed to put numbers. Right? Either right before the very first thing, things separated by plus signs, right after an arrow, right? We can't split these up in any other way. We must put before any molecule. But now when we look at this, we've got 2 carbons on the left, 1 carbon on the right. That's not balanced. We've got 4 hydrogens on the left, 2 hydrogens on the right. That's not balanced. We've got 2 oxygens on the left, but 3 oxygens on the right. And that's not balanced. Right? No part of this equation is balanced. So we've got some work to do to make sure that we can balance this thing out. The first step, the first thing I like to do when I'm balancing an equation, before you really get the hang of it and can start doing it quickly or start doing it in your head, it's really important to write out each piece. So I would look here, and with a pencil, I would go underneath each substance and say, okay, 2 carbons, 4 hydrogens. In O2, I've got 2 oxygens. In H2O, I've got 2 hydrogens, 1 oxygen. Carbon dioxide, that's 1 carbon, 2 oxygens. And also, put a line here to show me my left and my right, just to be certain. From there, we should have something that looks like this. And now we can start putting coefficients in and seeing how that's going to change our equation. The thing that is going to save you the most time, the most efficient way of balancing an equation, is finding the biggest molecule. Finding the biggest molecule and putting a 1 in front of it. In this case, it's my C2H4. Right, I get 6 atoms here, but there's only 2 here, 3 here, 3 here. So my biggest thing, the one with the most atoms in it, is going to be C2H4. So I'm going to put a 1 in front of C2H4 and see how that affects my equation. Right, putting a 1 in front of the C2H4 means I have 2 carbons and 4 hydrogens. But on the right side, I've got 2 hydrogens and 1 carbon, so that's not lined up nicely. I need to put coefficients in front of my water and my carbon dioxide in order to make me have 4 hydrogens and 2 carbons. What coefficient am I going to put in front of the water and in front of the carbon dioxide to make those numbers match up? In this case, it's actually going to be a 2 for each of them. A 2 in front of the water and a 2 in front of the carbon dioxide is going to adjust my numbers. 2 waters is 4 hydrogens and 2 oxygens. 2 carbon dioxides is 2 carbons and 4 oxygens. But now, my hydrogens are balanced. My carbons are balanced. So all that's left now is to look at my oxygens. So let's highlight those. Here, on the right side where I already have numbers, I have 6 total oxygens. So that means now I need some coefficient in front of my O2 to give me a total of 6 oxygens. The number that's going to go in front here for oxygen is going to be a 3. 3 O2s is 6 O atoms. And now, I've got a number in front of everything, and all of my pieces are balanced. I've got 4 hydrogens, 2 carbons, and 6 oxygens on both sides of the arrow. I have not created any new atoms. I have not destroyed any atoms. I've just rearranged them into new things. An important thing to know about balancing equations is it must be, by definition, the smallest whole number ratio. Which means I could put a 2, a 6, a 4, and a 4. I could double all of these numbers, and it would still be balanced. I would still have the same amount of each atom on each side. But that's not the smallest whole number ratio. Right? Smallest whole number ratio is what we started with here. It's also true of the formula we looked at before with making water. I can balance this equation by saying 1, 1/2, and 1. But this is not a whole number ratio, right? Half is not a whole number. And so I need to have the smallest whole number ratio possible. With this in mind, let's look at some practice problems. For this first one, before I dive in and let you take some time, for this first one, it starts balanced. That's totally possible. It is not super common for an equation to start off balanced, but it is a possibility. Here, a 1, a 1, and a 1 balances this out. I've got 1 carbon on both sides, 2 oxygens on both sides. Now that's not the norm, right? None of the rest of these start balanced, but it is a possibility, and I wanted to make sure I told you that. So now, I'm going to give you about a minute, minute and a half to try to balance some of these equations. And remember, just like always, pause if you need more time. When these equations are correctly balanced, they should look something like this. With our coefficients in front, making sure we have the same amount of each atom on each side of the arrow. Remember, right, take note of this pattern, right? Where can you put numbers? You cannot split up a compound, right? This Fe3O4, you can't split it and put a number in there. It doesn't work that way. You can only put numbers in front of the start of a substance. And you can tell when there are multiple substances because they are separated by these plus signs. Now I do have a second set of practice problems for us to look at, and so we're going to take a look at those too. But here I actually want to specify again about the first one. This is a much bigger formula. We got a lot of stuff going on here. In this formula, or in this reaction, we actually have some polyatomic ions. And with that, we get a little trick that we can use. Here, in this formula, there are actually 2 instances of polyatomic ions. I know how to write equations correctly by copying them, I promise. Right, we actually have 2 instances of polyatomic ions. We've got this OH, and we actually have this NH4. OH is easy to pick out because of its place in the parentheses. NH4 is a little bit harder, but it is still there. And now, these matter because when we break up our compounds, when I say this is 1 iron and 3 chlorines, I can actually leave polyatomic ions together. Instead of breaking this down into 1N, 1O, and 5 H's, which you can still correctly balance, you can break this down into 1 NH4 and a 1 OH, because on the other side, NH4 is still together and OH is still together. And that actually saves us a little bit of a headache. So when we come over here, we get 1 iron and 3 OHs, 1 NH4, and 1 Cl. And now instead of having to balance out N's, H's, and O's separately, we've treated them like polyatomic ions, which cleans up this whole process a little bit. Now when I look at what has the most stuff in it, I've got 4 things, 2 things, 4 things, 2 things. So I can actually start with either of these 2 substances and put a 1 in front. All right, we're actually going to start with a 1 in front of the NH4OH for this one because I want to make a point. A 1 in front of the NH4OH means that I have 1 OH. On the other side, there's no way for me to get 1 OH without putting a fraction in there. And I know I can't do that. So a 1 doesn't work for the NH4OH. For that same logic, a 2 does not work in front of the NH4OH. Because here I have 2 copies of OH, and I have only units of 3 here. So I still can't put a fraction in front. And so a 2 doesn't work for the NH4OH. When I put a 3, that means now I have 3 NH4s and 3 OHs. And now all of a sudden, these are balanced out. So that works. 3 NH4s mean I need to come over on the other side here and put a 3 in front to make these 2 into 3s. Now all of a sudden these are balanced out. And also, coincidentally, the rest is balanced out too. 1 iron, 3 chlorines, 3 chlorines. When a piece, right, when the biggest piece of your reaction doesn't work with a 1, you just slowly roll up the numbers. If a 1 doesn't work, you try a 2. If a 2 doesn't work, you try a 3. If you jump, if you're like, oh, 2 doesn't work, let me try 4, you're going to skip over the correct answer. And you'd be surprised how often people do that because they're in a rush to get to the right answer. If you're slow and methodical, you will always correctly balance your equations. Now, with that being said, I want to give you another opportunity to balance some equations here. So I'm going to give you another minute, minute and a half, and please remember, pause if you want more time. When these equations are correctly balanced out, you should get something like this. With all of your coefficients as the smallest whole number ratio you can get, not splitting apart compounds, not splitting apart molecules, only putting numbers in front of each thing. And with that, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.